Hi everyone and welcome to a new video about digital controller design. This is all example number 4. In this example we will discuss the PID controller design in the digital domain. We have seen in the previous 3 examples the PI and the PD separately. So we combine now the knowledge there and we make the PID controller. Of course we will do that in the calculation step by step and also verify these in MATLAB simulations. So let's look at our example. We have the design of a digital PID controller such that this system must have a settling time of less than 0.5 seconds. The overshoot must be also less than 25%, and we would like to have a steady state error 0 for step input. That means the position error must be 0. The sampling period for this system is 25 milliseconds. You see in this diagram the PID controller here, which is already in the Z domain. We see the sampling here and the hold operation to hold that sample, and also the plant here in cascade. So these 3, as discussed in the previous videos, will be the transfer function of the Z domain of the plant. And this sampling is here required in front to sample the input, the reference, and also the measured value at the output. The plant transfer function is here shown in the Laplace domain, which is a second order system. So let's see what we do in our solutions. Step 1 is the design point in the S domain, which is our design point given here in the general form, the real value sigma d and the imaginary value omega d. From the specifications we can determine the sigma d and the omega d. Sigma d is a real value which is then determined from the settling time criterion. Settling time of 2% criterion is equal to 4 over sigma d, so that means the sigma d is equal to 4 over the settling time, or 4 over 0.5 is exactly 8 radians per second. The imaginary value will be determined from the overshoot specification. For that we need to first determine the damping ratio, so the 0.25 MP, which is overshoot, as a scalar, and a damping ratio zeta can be determined using this formula by using this MP value in the scalar form. And when you substitute now the value in here, you get 0.404. Now for the imaginary value omega d, there is a geometric expression here which comes actually from the geometry in the root locus plot. You can see that sigma d is in here and the tangent of an angle which is determined by the arc cosine of this damping ratio zeta. Now when you substitute now the value in here, which is 8 for the sigma d, times the tangent of the arc cosine of this 0.404, you will get 18.5 radians per second. Again, sigma d and omega d have the units radians per second. Now our design point in the S domain is done. We have now our design point. Now the next step is conversion of this design point from the S domain into the Z domain, such that we can continue with our analysis in the digital domain. So the exact expression for the transformation from the S plane to the Z plane is defined by this formula. So the Z is equal to e to the power st, where the capital letter T is our sampling period of 25 milliseconds in this case. So when you now substitute this Sm here and also the T, specifically to get this Zm, which is our design point, we can now have the following expression. So you see the Sm here and also the 0.025 for the 25 milliseconds. Now when you work out the parentheses in the exponent here, you get this. So e to the power minus 0.2 plus j 0.4525. Now we can use the quantity or the characteristics of the splitting of the exponents. So multiplication when you have the same base, which is actually shown here. And now this e to the power minus 0.2 can be calculated, which is an approximate value. And this here, the second term, e to the power j 0.4525, can be written in the sine and the cosine term using Euler's formula. And that's shown here. So the first one is e to the power minus 0.2, which is this, 0.8187. And this part of the parentheses, the cosine of this angle, which is in radians by the way, plus the j of the sine of the same angle is using the Euler's formula. Now when you now work it out, and remember you need to use your calculator or your simulation program in the radians, so you will get now this and when you now work it out, you'll get now the design point, which is 0.736 plus j 0.358. That is now the step towards the design point in the z domain. The holding operation, let's continue with that one, is given already in the block diagram here, which is the transfer function here. So GH is a transfer function for the hold. And that's required in order to hold that sample. And this hold is a zero order hold, which says it samples a specific value and it holds that linear as actually a horizontal line. So that is the most simple way of holding a specific sample. So the sample and the hold and the planned transfer function together will make that z transform of our plant. So the GS, the total transfer function here, is then the hold times the planned transfer function that is shown here. Now we can rewrite this in this format, so you can get this as in the denominator here, and also 1 minus e to the power minus st here. Now we need to take the z transform of this expression, of the sample, hold, and the planned transforms together. So GZ is our z transformed variation of our plant, which is shown here, and that is then expressed in this format. There is one thing we can do here in order to shorten our calculations. We can take out this 1 minus e to the power minus st outside this z transform operation. Why is this necessary, or why is this better? Because e to the power st is already z, so e to the power minus st is actually here z to the power minus 1. So when we do that, you get this, and you still need to of course take the z transform of this part, which is then 12 over the third order expression in the denominator. Now this can be now split in 3 fractions or 3 parts using partial fraction expansion in the Laplace domain still, and then take each fraction and then convert that to the z domain using the table for Laplace transformation to the z transformation. That can be done, and so I leave the details out. That is quite straightforward. So the result is the transfer function here. You can see that, which is our z transform of our plant sample and hold operation together. Okay, moving on. This is our z transform of the plant. This is our design point just determined, and we now start with the controller. First, the controller transfer function. Since we need a PID controller, it has the expression for the PID controller has 3 parts. One of them is the gain, K1. The other one is the I operation here, which is the K2, and that the sampling and the Z operation. And we have also the K3, which is our derivative operation. Now together here we have now the PID controller. This is similar to the analog domain where we have the K1 plus K2 over S plus K3 times S, and this is really similar to that one. So in this case you can compare that for yourself also in the Z and the Laplace domain. Now we can combine now these 3 terms by making a denominator exact same, so we can get a common term by multiplying this with a specific parameter or a coefficient. So that is really straightforward, and then taking that together you have now this expression. Now what you see is we have now already a second order expression in the numerator, and there is a second order expression in the denominator. So we see there are 2 poles and 2 zeros. That's already known here. Now when you continue further, you can see that more clearly. This is now a second order polynomial in the numerator, so you see z squared here. You get also z squared here, and you get now our 2 poles, 2 zeros. Now, if you continue, you can also make it in this format. So you can see the k here, which is a new parameter, which is our PID controller gain, which is related to k1, k2, k3, and also the sampling period. And the rest are shown here. So again, this is the transfer function having 2 zeros, 2 poles. Okay, moving on to the digital PID controller design steps. In this case, I will proceed in the following steps. We determine first the location of one of the digital PID controller zeros from the specifications on settling time and overshoot. Now for that, since this is settling time and overshoot, that's actually sort of the speed characteristics of our system, we assume then the digital controller as being a digital PD controller. So we skip for now or use the I integration part later. Now, once we have done that, when is that completed, we will add the other 0, which is from the integral part, and we will do that such that the phase contribution of that integral part is not that significant, and we will see that shortly in an example. That's the second step. Now, the digital PI0 and the pole location can make the system a little bit slower than expected. So we can focus on 0.5, but you could maybe get 0.6 or 0.8. Now, in order to get your exact or required specification, you can tune the digital PID controller to meet all specifications. So this is the third step if required, but we will do the first two steps definitely, and where required we will also do the third step. Okay, digital PD controller, that's actually shown here, from here I mean, and that is only taking the part where we have the dynamic, so without the gain. So you see the PD controller, it's shown. The ZD here is our PD controller 0, and it has a pole at the origin. The PI controller transfer function in the Z domain is shown here. It has a 0 at ZI and also a pole at 1. Now, the digital PID controller transfer function is now the combination of these two in cascade times the gain K. So together you have actually this one. So K times the DPD times the DPI. And that is then shown here. So we see again now in a more convenient form that the K values are PID controller gain, 2 zeros and 2 poles. And that's actually shown here in a better form. So we will work towards the values of ZD, ZI, and also the K. So we have 3 unknowns here for our PID controller. So let's continue with our step 1, which is, as said, we assume that this system is now PD controlled, so the integral part will be added in the second step. So Root-Logos equation, we will use that. That means the 1 plus the loop transfer function, assuming that this is a PD controller, is 0. That means the PD only times the transfer function of the plant in the Z domain is 0. Now we know it is only the Z minus ZD over Z, and the transfer function of the plant is shown here, which is just this. Taken together, we have our expression for the loop transfer function. First, the angle condition. For that, we first make a drawing of the Z-plane, real and imaginary values. And we also set the zeros, the pole and the 0 of our plant, which is 2 poles and 1 0, which is shown here, which are shown here. So we have this 0.8607, 0.9512, and the minus 0.9355. So the 0 is a circle and a pole is a cross here. Okay. Now we need to determine the contribution of each pole and 0 at that design point, which is shown here in green, which has a real value of 0.736, which is here, and an imaginary value of 0.358, which is shown here. So how do we determine now the contribution using angle condition? Now we draw a line towards that ZM from each pole and 0. So that's shown here, that's shown here. So the angles are given by the phi 1 here, phi 2 always counterclockwise, and also phi 3 here. So we need to use these 3 phases and also the required phase that needs to be added by the PD controller, such that we get the condition for our angle condition, which is minus phi 1 minus phi 2 plus phi 3 plus the phi PD is equal to minus 160 degrees. Why is this minus phi 1 and minus phi 2, but this is plus phi 3? Because the pole location will contribute negative phase and all zeros will contribute positive phase. That is the reason for having a minus and a plus here. And this is the addition we require in order to get here to the left side and the right hand side exactly equal to each other, which is then minus 180 degrees. In this case, the PD phase contribution is equal to the 0 of that PD action minus the pole phase contribution of that PD action. So that means this location, which is at the origin, shown here, is actually our pole location of our PD controller. Now that phase is here already given, which is phi PD, so we can determine that already. But let's first determine the phi 1, etc. So phi 1 is determined by looking actually to the complete phase here, which is 180 degrees, which is a half circle, and we subtract this angle from the 180 degrees to get this phi 1, which is shown here. Now, in order to get now the this angle, you do actually arctangent of this height divided by the distance here, which is then 0.8617 minus this, which is shown here, and you'll get 109 degrees. Now, in similar form, you get the you do that for the phi 2. It's shown here, so it is 121. And the other one is the arctangent of the height here. In this case, it is actually an angle which is smaller than 90, so between 0 and 90. So you don't have to do the 180 degrees minus the arctangent. So this is not shown here, and this length here is then 0.9355 plus this 0.736, and that will be then 12 degrees. Now, we have now completely this expression here, except this phi PD. So how much is the phi PD? Yeah, you can now do the calculation for yourself, that's 38 degrees. So we need to contribute by our PD controller of 38 degrees. Now moving on, we know that the phi PD, which is this angle, it can be already calculated using the geometry here again. So the triangle with the right angle here, just geometry. We have now the height here, and we have this distance, which is 0.736. That will be then 26 degrees. Now we know that the difference here, so the zero of the phase of the zero of the D controller minus the phase of the pole of the D controller is equal to 38 degrees. So that means, that's shown here, that means the zero must be then 38 plus the 26 degrees, which is then 64 degrees. So we need more phase by the Z controller. That means also the zero must be also close to that vertical green dotted line here. So that means the following: tangent of that angle, which is just determined 64 degrees, must be equal to this height divided by this distance, which is to be determined. That is then this number 0.736 minus the zero location of our PD controller. So when you now work it out and express the ZD in terms of the other parameters that is shown here, and we now substitute that angle of 64 degrees, you will get 0.561 as our zero location. So we have now one of the unknowns of our PD controller, and actually one of the unknowns also of our PID controller. So our PID of PD controller 0 is shown here, and that's the zero location, and that is its phase. And that means the PD controller is shown here, and the 0 is determined. So we now continue with the step 2, which is adding the integral control to the design PD controller in step 1. Now for that, we need to know that a digital PI controller will add a pole at the origin, or at 1, I must say. And we need to place the PI controller 0, which is the ZI here, close to the PI controller pole. So in order to have a very small phase contribution, so that negative phase contribution by the PI controller must be insignificant. So if you place, for example, your 0 at 0.5, for example, it means that you have a lot of difference between the pole location and the 0 location. So in this case, I will select that 0.97, very close to that 1. You can also take maybe 0.92 or 0.95 or maybe 0.9. You need to see that in the simulation and also tune that if necessary. So then the transfer function of the PD control, which is very simple here and also very fast determined, is this. So we have now Z minus 0.97 over Z minus 1. Now we have now the complete zeros and also the poles already for our PID controller. The only term we need to determine is our K. So digital PID control transfer function is shown here as said. This is now the complete thing, and the K is only unknown. And now we are really close to our final result. So let's collect them together here. I'm moving on to the root locus equation, in this case PID control system, and that means again the root locus equation, but now for determining the K. And now we set up the equation here now with the PID controller DZ, and that is the expression here. Now for that we need to first then set up the magnitude condition. That means this coefficient here needs to be determined in order to have 1 plus k times this is equal to 0. So the k must be then minus 1 over this complete coefficient with them flipped. So it's actually shown here. And we need to now evaluate this k, parameter k, at that design point, Zm. That's shown here. So we substitute for the z, Zm, 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 Zm. So we see the Zm's here where we see a z. And when you now substitute this value for the Zm here, you get this long expression. Of course, you can simplify this because you see the real values here that can be then taken together and then simplified. Also, other parts have that. So when you do that, step by step, I have done that for you guys, and you have this expression. Now, we need to determine the magnitude of this expression, which is then using the magnitude of each complex expression. So the square root of this squared plus that squared, so the real and imaginary values, similar for the second one, the third one, and then the fourth one, and also for the denominator. And when you do now the calculations carefully, you get 56.3 approximately. That's now our gain. That means also the k is determined, and that means our PID controller is determined. So we have the zeros and the gain of this PID controller. This is the script I have used to evaluate in the simulator our calculated Discrete-Time PID controller. The script says the following. We have here the S parameter, Laplace parameter, the Z parameter definitions. This is the transfer function of the plant, which is shown here. In the S domain, this is the parameter for the sampling period, and this is the important command here, which converts this GP into GZ in the Z domain, which is then called continuous to discrete time transformation. The first entry is the S domain plant. The second is the sampling period, and this is how we do the sampling and holding, which is actually using the zero order hold. That means zero order hold, so that is the definition for that. The K here is our calculated PID controller gain. ZD is the PD controller 0. ZI is the PI controller 0. And this is the transfer function of the DZ, which we see here. Now, together we have now our PID controller. And this is the TZ, which is the feedback closed loop transfer function. So the feedback command will use the forward gain, which is these in the first entry. In the second entry, the gain or the block we have in the feedback, which is just 1. That's why we have 1 here, and a -1 is here to have this negative feedback. Okay, that's the script. You can use that to check this also for yourself. Now, first the simulation results with this initially determined or designed PID controller. This is the design point. The left side is our unit step response. The right side is our root locus plot. You see the unit circle here in black here. You see also in pink dots the closed loop poles and also the zeros here and poles here. And also there's root locus actually in blue. Let's first start with the design point. That's shown here, the current location, which says here 0.747 plus 0.369i or j, which is actually very close to that design point what we had anticipated. But let's see also the performance of our unit step response. The first one is shown here. The second one is the overshoot and the peak time and also other values. We see the settling time here and also the final value. Now from here we see the following performance. The settling time is 0.516 seconds. So larger than 0.5, that is definitely not fine. We see also the overshoot is 38.5%, definitely much larger than 25%. But the steady state error is 0, so that is good. So one of the three is succeeded. So we said this is fine, but settling time is definitely larger and the overshoot is much larger. So we need to also solve these two problems. But let's see what we can do. We can tune our gain of the PID controller. We can adjust the 0, one of them. It depends on where you start. The gain is always the easiest, so I start with a gain and see how far I can go. So the first adjustment is tuning the gain. And I have actually now changed the gain from 56.3 to 25.9. The rest is the exact same. Now we get a new root locus plot, new unit step response. I have actually done this such that I have one specification also met, which is done in this case the overshoot. So you can see here again the current location, which is 0.844 and plus 0.246i, which is different than that, so it is some variation. But the most important thing is unit step response. We see here the overshoot, settling time, and also the final value. The performance now here is settling time is even larger, so we made actually that problem even bigger, so 0.677 seconds, which is larger than the 0.5 seconds. But the overshoot is now at the edge of 25%, so that is okay. Instead, the state error is 0 because the final value is still 1 because we apply a unit input step. So we solved the second problem. So this is fine, but this is still a problem. So how can we solve that? In order to solve this, you can try to lower that gain or increase that gain, I must say. But if you increase the gain, then the overshoot will again increase, so they are actually conflicting with each other. So we need to make a more dynamic change here. That is the change in the zero. So I will keep this 0.97, but I also want to change the zero. So I have changed this zero, made it actually larger, and also adjusted afterwards also the gain. So we have now two things we do. So we simulation result with the controller gain and one of the zeros tuned. This is again the same, you see that? This is shifted from 0.561 to 0.65, and also I also adjusted the controller gain here, which is in this case 51. Again, a root logs plot and a unit step response. Now the current location here, which is now very close to what we have here, but still some variations. But the most important thing is again our unit step response. You see the overshoot, settling time, and also the final value. The performance here is settling time is 0.478 seconds, so smaller than 0.5 seconds. 25% for the overshoot, also at the edge, but still okay. And our set error is 0 because the final value is 1 for a unit step input. Now in this case, you see that this tuned PID controller will do the job and that meets the specifications. You can of course continue and make this maybe smaller or larger, or adjust the other zeros, maybe to get that even better, maybe to 20% overshoot or maybe 0.4 seconds as our settling time. That can be done. That is for you guys to experiment in more detail. But this is after 2 tuning steps, we got our specification for this example. Alright guys, this is our fourth example about the digital controller design. In this case, the fourth example discussed the PID controller. So we covered actually the complete set of P, PI, PD, in this case also the PID in this 4 video series. If you want to learn more about the design of the PI and the PD and the P controller in the digital domain, you can look at the first 3 videos in the series of the digital controller design. If you have any questions, comments about any other videos or these videos, just let me know in the comment section. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.